This also is Vincent Pasquier from Pasquier, time discretization of classical integrable models.
Thank you very much for inviting me. It's a great honor for me to talk at this Baxter conference. So I will talk about very simple things, which were not so successful, I must say, but maybe talking about it will give some new ideas, I hope. So this is some work I did with a big Slovenic group, Enej Jelinski, Thomas Prozen, Žiga Kranik, and some French people, Benjamin Herry, Grégoire Miskisch, and the German guy, Johannes Schmidt. Maybe this is the most important picture I would like to show in this talk. So this is Canberra 36 years ago. And actually, it was really a great time, I think, in physics. Just to say, conformal invariance was just being flourishing. Baxter, Forrester had discovered their Andrews-Baxter-Forrester model, and somehow the ideas were merging. People were understanding the connection. So the minimal series was really the same as what Andrews-Baxter-Forrester had been doing. Vaughan Jones, who is actually on this picture and who unfortunately also passed away, had discovered the knot invariant. And I shouldn't forget Bajanov and Stroganov, who had started understanding connecting the Karol Potts model to Baxter Q matrix and the 6-vertex model. And I still remember Vladimir Korepin arriving and just getting out of the plane and explaining to everybody these new things. So it was really exciting and something. Well, maybe Murray can check. There are still 10 papers which are on this picture, and so although it's 36 years ago, who are talking at this conference. At least 10. Maybe there are more. I don't know.
I will count them. Yes.
Sorry.
I will let you know. I will check.
Oh, you'll check. Okay. Thank you. Thank you. So now my plan is to, well, first I will give my motivation, then I will describe some very simple discrete classical integrable system, and in particular connected to Baxter's ID, the box-ball model, and then the Toda and Landau-Lifshitz, and some critical models which break Lorentz invariance. So my motivation, we want to study transport out of equilibrium in quantum and classical systems. This is really what we would like to do. We would like to make some progress on time correlations in the integrable models. So this is a very, very difficult problem, I must say. Not really much progress has been done in this direction. And also, we'll find, of course, analytical results in integrable model and somehow understand the difference of physics between integrable and non-integrable. I mean, what do we learn by studying an integrable model? And in particular, the most interesting quantities which we would like to study are the spin correlations, of course, I mean, or any correlation, density, whatever, and in models which have conserved charge, the charge transport. So let me remind you some basics idea which actually come from Rodney Baxter. So really the main object which he introduced, and well, maybe Lieb and other people had introduced before, is the vertex. So just you can think of this vertex as a positive Boltzmann weight, or at least that's what Baxter was considering. But you can also view it as a matrix. And if I follow the red arrow direction, it's a matrix which takes mu sigma into mu prime sigma prime. And you should, I mean, it's interesting to look at some different cases. So it can either be positive, but it can also be stochastic or unitary. And so this could describe probabilistic evolution, if you want, or, and that's what people have been also trying to do, unitary evolution. So then, once you have this this weight, you just assemble them together into a partition function. And when you glue them, of course, you need to sum over the indices. So you can think of this partition function as a big matrix, if you want, which takes you from the mu sigma variables to the mu prime sigma prime variables. So you could think of the time going in the diagonal direction and some initial condition on some light cone. And then you want to study the final states, which are the new variables. And so if the matrix is stochastic, then this will give you a stochastic evolution. And if it's unitary, it will give you a unitary evolution. So it's a slightly different point of view. I mean, either you view this as a partition function, then you just look at it like that and you sum, or you can also view it as some evolution. And the point of view I want to have in this talk is rather the second point of view. So then, to compute this partition function, a really important object, which was, well, maybe not introduced by Baxter, but certainly used a lot and may make many discoveries about it, is the transfer matrix. So it's just a line, and then so here I describe the monodromy. You just specify a line and you view this as a kind of double matrix, a mu prime matrix and a sigma sigma prime matrix. And for example, in the 8-vertex model, sigma and mu takes the value plus or minus 1 in auxiliary space. And then, well, what really Baxter did is he looked at the closed transfer matrix. That is to say, he identified the mu and the mu prime. And then he realized that these were defining a commuting matrix. And of course, he had to introduce, so the weights now depended on a new parameter called the transfer parameter, spectral parameter. And these transfer matrices were commuting. And this is a very important aspect, which was not so important in integrability, but well, before, I mean, was not really emphasized. But the fact that they define commuting transfer matrices suddenly made a real progress. So now, if we make this identification, we consider a lattice model on a cylinder, if you want. And the matrices, the transfer commute, and so they can be the transfer matrix can also be viewed as a generating function for conserved quantities, because the expansion in powers of u are conserved by this time evolution, if you want. And so this somehow makes people ring a bell, because it really connects the field to another field of integrability, which is the lax matrix approach. And so suddenly these two fields, which were not talking too much to each other, started to really collaborating a lot. Some detail I would like to say is that stochasticity can be preserved by this transfer matrix evolution. And there were a lot of progress in so-called probabilistic integrable system. But as far as I know, when you start closing putting it on the cylinder, you cannot really preserve unitarity. So this is maybe some drawback, and maybe one of the reasons why these models have not been so much studied in the unitary context. Well, also another point is once the matrix is unitary, the spectrum is on the unit circle, so it makes things much more difficult also. So now, since it's difficult, I just want to try to simplify the problem and actually introduce the idea of transfer map, which really comes back to works of Sklianin, who defined the first transfer map, which I will present a little later. And then this was formalized by Drinfeld. So now it's just the same thing, but we look at the vertex, but we don't think of it as a matrix. We think it as a map. So what this means is that this L mu prime, you think of it as, so mu could be any object and sigma, and then you just have a map from mu to mu prime and sigma to sigma prime. And the same thing as for the transfer matrix, the vertices can be combined into a propagator by just putting them in lines, if you want, or combining them. And when you want to do a transfer matrix, as Baxter was doing on the cylinder, you should impose some cyclicity condition. That is to say, you should require that mu at the two and mu prime at the two ends of your chain should be identified. So it's very much the same as the transfer matrix, but now it's a map. So since it's fairly abstract, I would like to present a very simple model of such a map where really analytical calculations can be done quite fast. So this is the box mold model of Takahashi and Satsuma. And so you should think that there you have time evolutions, which goes upwards in your systems. And as for the transfer matrix, well, this is something which I did not explain, but you have two spaces, one which you could call the physical space, and the physical space carry just one ball if you want. So if you have one ball, you put a 1. If you have no ball, you put a 0. And then you have what is called the auxiliary space. So this is the horizontal line on my picture. And on the horizontal ball space, you put a certain, as many number, many balls, but bounded by L. So you call the auxiliary space the carrier. And so the carrier has n balls with 0, little and n, little L. And L is called the capacity. And the carrier, you so think of a truck, it goes through the system. And whenever it can pick up a ball, so on the first picture, then it picks it up. And so after that, the ball there is no ball. So, and it carries through. Or if there is no ball, he will try to give a ball. And of course, he will not be able to give a ball if he has no ball. So if there were only zeros, and he will not be able to pick up a ball if he's filled. So if there were 4-4-1. So it's a very, very simple model. And nevertheless, it's quite interesting. Now, as I said before, so that's what I learned, by the way, by Atsuo Kuniba, who explained us that model, and we worked on it with him. You must try to have cyclicity. So that is to say, you must made it so that the carrier carries as many balls at the last step as at the first step. And that's quite easy to achieve, actually. What you do is you just let the carrier pass through, look at how many balls he has after having passing through all the other balls, and just put it back at the origin. So then you put this number of balls, and then you're ensured the next, when you try again, that cyclicity will be achieved. So you just achieved, you must do a first round trip for nothing, just to get the number of balls the carrier should have in order to ensure cyclicity. So why is this model integrable? Well, first, having to do with commutativity of transfer matrix, you can really check that propagators, so what I call now the transfer matrix becomes a propagator with different capacity L commute. So this is the analogous of Baxter. And even more, you can really have conserved quantities because you realize that solitons, which are made of k consecutive balls, are conserved in number. So now, what about the physics of this model? Well, first, if you have, I encourage you to do this exercise. If you just look at one single soliton, you will see that it travels at a speed equal to its length, just by following the rule. But actually, when you have many solitons put together, they travel ballistically, that is to say, they with a certain speed, but not the bare speed, with a new speed due to the interaction with the other solitons. And this new speed can be exactly evaluated. And this is the topic of an interesting subject, which I would like to publicize, called generalized hydrodynamics, GHD. And it turns out that to understand the physics of that model, the really necessary ingredients are just the bare speed of the solitons and their scattering lengths. And the scattering length in that simple model of two solitons is just the minimum of their lengths, K and L. Actually, this formula, 2 mean KL, if you read carefully the first paper by Better on Better and That is already there. So this is really an old story. Okay. So in this model, time correlations can be evaluated. And just to show you a picture, so this is the time correlation, the correlation of the density-density correlation. And it's quite easy to understand, where when you make a density bump at the origin, and then this density bump will break into solitons that propagate at different speeds. So here you see 3 speeds, V1, V2, V3. And so at time t, you will see correlations at distance V1t, V2t, V3t, and actually each little bump carries a portion of the initial intensity, and this portion can also be evaluated exactly. So this GHD is quite powerful to compute things in at least in this ballistic regime. So now, so this is some work I did with Atsuo Kuniba, who is here actually in this conference, and Gregor Miski. So now I would like to go to another model, which is also extremely interesting and famous, the Toda Hamiltonian. So it's just particles which interact with exponential strength. And again, integrability results from a lax matrix. So if you think it's not really a vertex, but it's something very much like a vertex with 2 by 2 internal space. And if you construct the transfer matrix, which you obtain by taking products of these Li matrices, you discover the conserved quantities of the Toda Hamiltonian. So now I want to describe the vertex map. I want to describe, if you want, this integrable classical model. So you should think that time goes up. So you think have the same picture as for the box ball models, but now you don't have balls. You have 2 variables, x and little x and big X. So maybe I should have explained. I mean, you see, P, I call Pi big X and exponential Qi little x. It's just for me a little more convenient. So you have these variables that propagate in times. I put a bar on the top for the next time step. And then you have the equivalent of the carrier, which are the S variables, which actually also have a lax matrix called the discrete cell trapping matrix. So this is some work. Actually, Suris probably was the first one, and Sklianin also. And so again, like the transporter, the DHT variables pass through the TODA variables and update them. And as for the model of the box pole, we must ensure some cyclicity conditions. That is to say, the S variables must be the same at the beginning and at the end of the chain. So how to define the vertex map? That's the main idea of this model. Well, first you have to use the lax matrix for TODA, which was used to construct the conserved quantity, and also the lax matrix of the DST model, which is and if you want these two models, they are close cousins. They have the same R matrix, also they have the same Poisson brackets. But now what you do is you do what we call a Darboux transform. That is to say, you take the product of the two lax matrix in a certain order, and then you try to reorder them in the other way, so as to define the new variables. So I mean, you solve this equation, Li Ri equal Ri plus 1, L bar, that is to say, a next time step of U. And what it's very, very simple problem to solve, and you find. So here I express the big variables, x and little x, in terms of the small variables. So this is a small variables. And now the spectral parameter, I did not say it, but the spectral, well, at least the difference between the two spectral parameters becomes the time. And when the time step goes to 0, you can check that you recover the standard time step evolution. So that's a simple way to define at least the model. And now you must also ensure the cyclicity of the model. Sorry, and to ensure the cyclicity of the model, well, in practice, what you do is you do exactly the same thing as for the box pole. You pass the S variable through one time, but then you don't get immediately the cyclicity. But if you repeat it several times for a change which is long enough, then it converges to a periodic chain. So somehow you can have a Perron-Frobenius argument that enables you to achieve a periodicity, but actually you can do better. I mean, actually you can solve a second-order differential equation, second-order equation, not just a polynomial equation, which I will explain this a little better in the next model, which enables you to find this cyclic variables. One important thing, so I said that in unitary case it was as far as not possible to realize unitary at the level of the transfer matrix. But for the map, this is possible, and so it's not unitary, but it's simplicity. So you can make it a canonical map, and to show canonicity, you need to construct some generic function for the canonical transformation. So what this means is that if you look at this function f, if you take the derivative with respect to log of xi, you will find big xi, and if you take the derivative of log of xi bar, you will find big, well, up to with a minus sign, big xi bar. So this is the definition of this canonical transform. And I show you this for the expert because this is also related to Baxter. If you take the exponential of this function f, well, you recover, so it's a kernel if you want, and this kernel is exactly the Baxter Q matrix for TODA. So again, the famous work of Baxter is related to appears there. just to finish my presentation, I would also like to present another model. So this model is really interesting for TODA is very interesting, but this one I think is even more interesting for the physics. And actually, I guess it will also be discussed by Thomas Prosen in the last talk. So I will not say too much about it, but still I would like to talk a little about it. So Landau-Lifshitz, if you want, is a kind of continuous model for the XXX chain. So you have a spin which is a unit vector and which evolves with this equation. So it's a kind of classical equation of motion for the XXXP chain. It is, and this is something which is not so well known among physicists, it is obtained by something called local induction approximation to describe the motion of a filament in a superfluid. So to see the filament, you have to think that S is you have to think that you have a curve and the vector S, the three-dimensional vector S, so this curve is in three-dimensional space, is the tangent vector to the curve. And so this equation gives you the evolution equation for the tangent vector, or if you integrate it, the axis of the curve has this equation of motion. And so actually, in some cases, with some good initial condition, you can solve for this equation. So I just present some time evolution, which are which were discussed a lot by mathematicians, Banica, for example, De La Hoz, Vega, and maybe other people. And this is quite so. This is a quite simple curve to obtain. You start with a filament which is made of two straight lines, which make two half straight line, which make an angle, and then you let the time evolve, and this will create some kind of vortex, if you want, which is so this is time a short time, and now you see the time evolution. And of course, this is a projection. This is a three-dimensional picture, and so this is interesting to study in turbulence. And just to make things simple, to obtain this curve, you have to use the equivalence between Landau-Lifshitz and nonlinear Schrödinger equation. And in that case, it's not even nonlinear Schrödinger equation which you have to use, but just the Schrödinger equation. So from the simple evolution of the Schrödinger equation, you can obtain this time evolution. So now I get the technique. How do I define the vertex? This is exactly the same thing that I presented for TODA. I have to use the Lax matrix, which essentially is the six-vertex model Lax matrix, which you recognize here. And then you solve for so this is what Giga Kranik and Thomas Prosen did, but actually Sklianin had done this many years ago. So you look at this again, this equation with the time in the spectral parameter. And well, now you don't have two Lax matrices, you just have ones. And again, you solve this equation, which is not very hard. You find the time evolution of the spin, so the Landau-Lifshitz, and the auxiliary variables evolution. So here, so is the time step. Here is the evolution of V, the evolution of S in time. And now, why is this model interesting? Because it has a very curious transport. It's not a ballistic transport, or it's ballistic. Well, I mean, actually, we generalize this model for arbitrary delta. I did not talk about this, but many years ago, Thomas Prosen and Znidardijk had realized that the transport was anomalous. And so it was ballistic for delta less than 1. So they were looking at the XXZ chain, sorry, not exactly Landau-Lifshitz. As I said, Landau-Lifshitz is a kind of classical version. So it was ballistic, anomalous, And this anomalous means it was connected to the famous KPZ equation, Kardar-Parisi-Zhang at delta equal 1, but this will be explained better by Thomas later. And diffusive, but a kind of strange diffusion, which we don't fully understand for delta less than 1. And so from the Brownian filament point of view, in fact, what we would like, why we introduce this discrete model, because we would like to have some kind of initial condition where the Brownian filament is if the filament is a Brownian at time 0. So you imagine you have a Brownian filament, and then you let it evolve in time, and you should see this anomalous KPZ times of evolution. Unfortunately, at this point, I am not really able to say more than drawing you a numerical simulation. So the simulation I show you was done by Grégoire Mitgish, but other people did the same simulation, and you recover somehow. So this is a spin-spin correlation function, time and space, and you recover a famous curve obtained in the KPZ concept by Fraunhofer and Spohn. And so this is what we would like to understand better, but I must say at this, except, so actually the discrete model I described is not the only one. The one that Thomas had discussed is more like, well, if you remember, a 6-vertex model, not in the time direction, but in the light cone direction, like Ogzarek Baxter had studied many years ago. But I think the one I present has the advantage of exactly preserving the conserved quantity. So I think it's a little better for analytical studies, because we have this commuting, well, not transformatric, commuting propagation and so on. So my hope is that this should be enabled to make more progress. Okay, and this is the end of my talk. I would like to thank you, Rodney, for giving so much up to us in your work. Thank you.